Thanks, we finally got it going. I'll use the next 20-30 minutes for an overview of a work which has been going on for about half a year of actual implementation, and which had discussions prior to that in the machine kit tracker for at least another 1.5 years. For instance, the issues about HAL accessors and anatomic operations and so forth. So that goes back quite a long history. It is work which has actually been done by Mick Grant and myself, starting in summer, and it was when the discussion about how to revamp the HAL internals to make it safe for multi-core CPUs reached a point where we actually had a plan on how to go about it. I will concentrate only on the very high-level view. It is actually a massive rewrite of HAL, but it is fully compatible, and all the applications and configurations still run. So it was quite an achievement, and I'm very happy. I'm very grateful for Mick to chip in on this, and he has borne a lot of the work which made that happen. Although he couldn't make it because it's hunting season in the UK, and that has priority. Okay, just to recap what the actual causes to start that work were. HAL goes back 10-15 years. It is a great design, but it is a child of its time, if you will. At the time, single-core CPUs were the norm, and certain architectures were the norm. That picture has widened quite a bit, and especially since we have brought this onto embedded platforms, also onto ARM processors, which have a different memory model. There have been cracks in the picture, and that eventually needed addressing. And I think that work actually does that. So that's not a fault of HAL. It's just a set of historic assumptions which needs review every 10-15 years. We're still in line, or do we need to do something about it? And those are the core issues I found, which we would wanted to get rid of. First, the restriction, as already mentioned today, all the RT threads being accountable only against a single core, meaning the whole thing becomes unsafe once you distribute it across more than one core. That does, in fact, limit the budget on what can be executed within a real-time context, and it does become an issue. If you look at the BeagleBone, we're running in the real-time budget there about 90% of the allocated cycle budget at peaks. It's getting close, so any measure to relieve that is certainly welcome. Then one of the historic facts was HAL was built for the x86 platform, which has a very conservative memory model, strict ordering, and you get away with lots of practices which you do not if you're using an architecture which has a more looser memory model, in particular the ARM platforms, which we're using. So that's another fault line which appears, and it actually shows in the history. For instance, in the regression tests, as we move those from x86 platforms to ARM platforms, certain components start a erratic failure pattern, okay? But extremely hard to nail down. You try to reproduce them. It's a statistic affair. Phase of the moon, weather, load, software version, any number of reasons, but very hard to reproduce. So that was a typical sign of such a consequence of these memory ordering issues. Charles already alluded to that. The way HAL was, the HAL memory layout of actually of signal values, how that is done is very much oriented towards a single core. If actually HAL objects are accessed by more than one core, you get into that effect which you alluded to, which is called false sharing. There's a lot of literature on that, but it's basically contention on data objects which reside on the same cache line, but are in fact accessed by different cores. And that effect is visible already in single chip multi-cores, and it gets really worse once you get into multiple socket CPUs, because in that case the inter-cache communication actually goes through the PCB and external lines and becomes much slower. Some of the regression tests which we have introduced actually show that. We've stolen certain techniques from the concurrencykit.org software package, which is integrated into that branch. And to show such effects, what they have done is implemented regression tests which do core hopping. So a task tends to start hopping from core to core. And what you see it, as long as it lives on the same core, it just runs fine, and suddenly it drops by an order or 2 orders of magnitude in performance as it crosses onto another socket. Yeah? And in that case also, it's one way to trigger certain failure scenarios because the timing behavior suddenly changes. So that's one of the ideas which we successfully stole from there. So the summary there is the assumption about single core and cache efficiency, if you will, that was fine for the single core CPU. In a multi-core scenario, it's actually detrimental. What you want to do is to keep these values apart. However, these decisions about HAL object layout are in a very low level in the HAL library, so it's quite fundamental. So you won't get away with a one-line patch here, if you will. So it is a change of assumptions, really. The latest one is actually the nastiest one to fix in terms of work. That pertains to components which employ more than one thread to achieve their goal. Those are not many, they're about 5 or so, but they're the software step GAN, the PWM GAN, the encoder, and the SIM encoder components. That is one assumption in HAL, which I think is a little bit exotic. What has been done there is to use the behavior of non-preemptive scheduling as a means to synchronize access to shared state. Not logs, not log-free data structures, but scheduling behavior, namely that the higher priority thread would run to completion until done, and only then the lower priority thread gets its turn. And that behavior is the assumption between accessing shared state within these components. Now, if you have the case that you have multiple cores and you happen to to run these 2 threads on different cores, then well, fine, they have different priorities, but they are not preemptive in a sense that the lower priority thread gets to run because there's an idle core anyway. So in that very moment that the state synchronization assumption is violated, and then things go haywire in becoming inconsistent. So that is actually one of the larger amputations there, to switch those components to a thread-safe state synchronization model. So that covers basically the set of things which needs addressing. To do so, to look at examples where the things actually go wrong, I'll give you a short demo of a regression test, which will be a bit of a surprise. You'll probably just think of of a variable, a pin, an I/O pin in our example case, and you have one thread up incrementing the value of that pin 40,000 times by 1. Well, at the end of that run, the value will be 40,000, right? Okay. Now, if we do the same thing with 4 threads and each one 10,000, what's the result going to be? 40,000? Well, hopefully. The real answer is depends. I'll switch to a short demo of the regression test, which actually shows that this is not the case. I hope this is visible. That is a part of a regression test which was added to the code base. It's actually a C-based regression package. Okay, I think we need to slide this to the right somehow to make it fully visible. Okay. The highlighted area shows the result of doing exactly that operation, incrementing an I/O pin by 4 cores in a loop, and each loop does it 10,000 times. The interesting lines are the third one, the first highlighted line tells you the result with an existing legacy I/O pin, meaning not even half of the updates actually happen, because that's the way the read increment write operation, that's how that fails on if in presence of multiple cores. If you actually protect that operation by memory barriers, that doesn't change a whole lot. It does get better, but does it actually? No, it's actually worse. Okay, but still we're not there. The picture really only clears up once we introduce atomic operations. I think I used 2 different libraries there, the GCC atomics and the atomics from concurrency kit, and 2 different atomic implementations using a compare and swap operation. That isn't relevant anymore, but the key result there is you get that result only if you use atomic operations. There's no wiggling around with memory barriers. So that's an example where a very basic pin operation fails in the presence of multiple cores. And that's certainly not something desirable. So, okay, let me get, I hope I managed to get
those are atomic read, modify, writes. The read and the writes and the legacy are atomic. It's the reading and changing and writing again that's not atomic.
Yeah.
So.
Okay, let me see if I can make it back to the presentation somehow. To Alex.
That's actually why it's worse when you enable the record. So just the time between when you read it and when you wrote the value point plus is longer. So you've got more time to record and step over it. So yeah.
Oh, okay. That's an easy one. So that was the first one. Even basic pin operation. I mean, you might say incrementing an I/O pin from multiple threads in a loop is a bit exotic. Well, yes, it is, but it still shows there's room for improvement here. Another scenario where that clearly showed up in the regression testing as we extended towards ARM platforms were components which employ handshaking pins. So a typical one is the I/O control component, where there are 2 pins in sequence, changed in sequence. The first one, the new tool number is set, and then a signaling pin is raised, saying, by the way, the new tool number is now valid. And that's exactly the point where memory ordering can come in, and the reading process gets an old tool number. That's something which needs to be fixed with a with a memory barrier. So we have different effects, and we need different tools in the box to deal with them. One is the atomic operation at the pin level, and we need sequencing between pin operations by memory barriers. The third area Charles already alluded to. That is the realm of handcrafted queues in the Linux CNC code base. Those are in particular the sampler and streamer components, which are prone to sudden failures on ARM platforms. And we never really got the hang of it until it became clear that it was exactly the failure scenario that Charles was describing with a missing fence operation before the update. Unfortunate with these components that each of them, since the legacy code base had no good queue abstraction, all these components had their custom implementation of queues. So that isn't the case anymore. We have a common ring buffer code, which is reviewed and robust and hasn't shown any problems. So the best way forward there is leave these components as is and just create a new one with a new ring buffer code to take care of that. That doesn't need any change at the HAL level, actually, but it needs at the HAL API level. But it is one of the problems emanating out of missing atomics and memory barrier operations. It does require, however, that we have those primitives available. That has become available in various forms and shapes in GCC over recent years. It has trickled into the C11 standard in a specific form. Then there are a large number of libraries for such operations. Not all of them are created equal, especially when it comes to support of multiple platforms. Many of them seem to focus on one platform only, like AMD64 only. So there's some leeway which ones we use there. Fact is, in the legacy code base, there was nothing at all. And the last one I already alluded to, the dual thread functions, the dual threaded components, those need actual rewrite on the state access level, how we can deal with those with an actual concurrent invocation of thread functions. That is something which has been achieved already as well. Okay, so to summarize on what a list of issues is and how we deal with them is now in the field of pin and signal value consistency, we need to go towards atomic operations. That has some dire consequences. In particular, the API which you currently have, namely the pin being a raw pointer, and you just dereference the pointer to change the value it's pointing to change the signal, will not be sustainable. We'll have to drop that. We had a long discussion on that in the tracker. The way to do that is to go towards a more object-oriented representation, to use not the raw pointer, but a reference to a descriptor, or a class instance, if you will, in C++ talk, and use accessor functions in that class to actually achieve the operation as it is needed. So that's about the use of atomics. That's unfortunate because there are lots of pins being used in HAL components, but we'll have to change the API to get that fixed because the raw value, the raw pointer which is passed by the legacy HAL API is insufficient to address that issue. Now, so that's the atomic part. Hardening against load store reordering. We need memory barriers there. And the way that has been addressed is pin signals and also thread functions can have attributes with respect to memory barriers, meaning before a thread function is invoked or after it terminates, a memory barrier operation can be executed, a read barrier before it started, a write barrier after it's finished. That is at the thread function level, And again, we have the same at the pin level, which is finer granularity. But then in that case, it goes against every pin operation, so it has a higher cost involved. So all these are available at the HAL command level or at the HAL pin C API or Python API level. And that is a runtime settable property. You can change it on the fly in HAL command, whether a memory barrier is executed, a read barrier is executed before operating on a pin or a write barrier after executing on a pin. So that covers the atomics and barrier operation. So by what we've done there is providing attributes in the HAL descriptors, which say which ones of the barriers should be executed conditionally if the function is invoked or if the pin or pin is dereferenced. So that covers that part. The more complex part actually being the synchronization by scheduling policy part. How do we get rid of this preemptive scheduling assumptions about state synchronization? Now, the top level answer is to use log-free data structures. As we go down on the concrete components, we can distinguish a couple of scenarios. Sometimes a very small, it's only just a very small value, maybe just an int or a double, which needs to be shared between those thread functions. In that case, it's trivial. You just use an atomic operation there and be done. Sometimes it's also possible to pack some of the smaller objects, like it's a couple of booleans or flags. You pack that into something which is less or equal 64 bits, use an atomic operation on that, and then you're safe, okay? In the case of that is not sufficient, out of those 4 components which I mentioned, one component got away with a single 64-bit atomic. The others needed a little bit bigger barrel to address the issue because the amount of shared state between the functions is larger. Now, basically, there are 2 scenarios on how that state sharing between thread functions works. First is an update scheme where every update counts, like an incremental update, and it's being summed up in the receiving entity. The other one is, it doesn't matter how many updates there are, only the last one counts. So these are the 2 patterns, and depending on the 2 patterns, there are 2 software vehicles which we can use there. It turns out the components which we fixed there were all of the second variety. The updates between the threads is only last value counts. In particular, StepGAN has a rather large shared state structure there. And to do that, John is probably going to like that. John else. We found a very elegant data structure and log-free implementation for a triple buffer. The read side has always a buffer which it can write to, and when it's done, it flips the buffer and basically makes that last copy available. And the reading side may check, is there a new copy? And if the answer to that is yes, it atomically copies over or switches to that last updated copy. So that needs 3 buffers and some coordination with an atomic variable that is all farmed out in a single header file in maybe 100 lines of C. It's actually comprehensible. And it's a very robust scheme, works fine. And that was enough to take care of the state sharing between all of these components. It took 3 attempts to get those 4 components right. The first one, and the problem with those were the instance data of these components is actually huge. There are 50, 60 variables that, which live in a per StepGAN instance. And there was no separation at all which data elements are used by one thread function, by another thread functions, ones which are only setup time information and never used again, or which are actually shared state. And so a first iteration, Charles reviewed kindly and said, okay, that failed because you overlooked this. For 2 or 3 of the components, there were obvious errors, but just trying to manually sort apart which state elements are updated by which thread function. So I switched to a different approach and actually separating the state into separate structures. So it's syntactically impossible to have sharing between thread functions if they are not in the proper structure. And that one actually worked, and it turned out we found a couple of more pieces of shared state which previously had evaded the inspection, but essentially used the compiler to separate it all, and that worked. So it's now four elements of state, config time only. That's pretty harmless. It's one thread function, the other thread function, private data, and the shared data. And the shared data is the one which you need to address with either an atomic or the triple buffer, and then it becomes relatively straightforward. But the rewriting process of splitting up the state and so is a somewhat painful operation. So for the complex ones, that has been achieved. The last issue was the false sharing of HAL signal objects, because the way it's currently done, they're all tightly packed together with a custom memory allocator, which was beneficial in the single RT thread core, single core, single cache setup back then, which is detrimental now, and or in a multi-core setup. And the way we've addressed that is to actually get rid of the explicit allocation of memory of signals, which you have in HAL, and move the memory, which was previously explicitly allocated, into the descriptor structure of the HAL signal. Turns out the descriptor structure is something between 50 and 128 bytes, but it's typically larger than a cache line. So it's a safe place to store. And if you add it there, it will be isolated from all the others. So we squat 2 flies in one go. We get rid of the separate memory allocation step, and we cache pad them against each other. And that is actually also how the legacy compatibility mechanism works on the pin level. If we don't give that function the address of a piece of data where the pin, the pointer, actually lives, that function will return a handle which can be used for the version 2 API functions, including memory barriers and atomics. So the API can be used for V2 or for the version 2 API or version 1, and the pin operations are all interoperable. Okay, so there's no change in the semantics for V1 components, and it does not break. So that's the list of concerns and the mechanisms how it is addressed in this work. That is only the part which pertains to multi-core and atomics and barriers. It was actually a large cleanup operation because in this we completely reorganized the way HAL objects are organized. In particular, the API does not export anymore all these list pointers which are needed to iterate over HAL objects, of which I think we deleted about 100 or so custom iterator loops, which are in the typical find or loop over an object type function. And those are all replaced by a single iterator, which covers all of that. The internals are not exported anymore. The change is quite massive, but the configurations run unchanged and all the regression tests pass. So it is possible to retain compatibility. That is just the changes under the HAL subtree. In terms of status, where we are, I think we all owe a lot of thanks to Mick Grant, because he's jumped in and helped me with this on the component level. I worked on the API, and he took on of migrating the components, in particular the inst.comp tool, or comp tool, or HAL-compile as it's called in Linux CNC now. That he adapted to generate the V2 API calls, and to convert components, because the components still used raw memory operations, so you need to explicitly add wrappers. But all the components have been rewritten and are available for this new pin semantics. So that is for the components, the .comps. That is not available for the ones written in C, obviously. For in C, the tough ones with the dual thread function components, those I rewrote. These are cleaned up, so we have a V2 version of those. And then there are a couple of C API components which still need to be converted. The largest one being actually motion. However, for our intents and purposes, it is an uncritical component, as it is a single thread function component. Okay, and we'll eventually get to it, but doing the conversion step is quite a mechanical job, and most of it can be done by an editing script. No surprises. Mick has converted a lot of those, and we have no reduced need for coordination on that level. With it went a lot of other improvements. I'm just running through it to see that not all of these changes were caused by the multi-core stuff. The internal API cleanup, it's much more simple to add or loop over objects. We removed a couple of red herrings along the way, because working on these primitives, because of the frequency of their being executed, it is paramount to know the execution times, especially for the high frequency operation of pin changes. So there was we did quite some timing analysis. Among them, one of was taking timings of the time-taking functions, because those have overhead as well. If you look into HAL command, you see time indications, but it's unclear which unit that actually it is. It doesn't say so. Funnily, this is called clocks. There's an API RTAPI function called RTAPI get clocks, and that gives you something in a mythical unit called machine clocks, which is basically the clock frequency on x86 and AMD 64, but probably something entirely different on ARM platforms. At least it's not, the unit isn't specified. So the clocks are only of relative value. There are two clocks functions. The get clocks, which goes fast but doesn't tell you exactly what the unit it is, so it's less than helpful. And there's one which actually gives wall time, but it's a more expensive operation in terms of runtime. At least that's what the legacy code base says. So I thought it's time to review that, if that is actually still the case. And it turns out on the ARM platforms, both implementations use the same underlying system call. So there's no reason to distinguish, because they have the same runtime anyway. And on the fast platforms, it doesn't matter. So we could just as well do away with it, and we now get actually times in microseconds and nanoseconds, which is much more helpful than these funny clock units. Along the way, HAL got a heap memory allocator. So HAL free and malloc is actually supported on the shared memory level. And along that way, the HAL name limit just was raised because it's not relevant anymore. There are some changes which already trickled back into the machine kit. For instance, the idea of throwing a core at a job, if you will. You take one core and you just let it busy loop on a task. You don't have it actually wait for and do a cyclic execution and say, okay, I'll forget about it. I just have that execute as fast as it can. And that is already trickled back in the machine kit code base. You can, here's an example of how to create such a thread with a no-wait keyword, and you bind it to a specific CPU. That is actually a POSIX thread, so it does not account against any RT budget, but it will, on a Raspberry 2, execute with about 150 kilohertz on a single loop function. There is an issue with that, as Linux currently requires even a core which loops to be rescheduled once for some householding, about once a second. So every once a second, we get a little dip in the response time of that cycle. However, that is being taken out of the Linux kernel as we speak. It is called the no hertz idle full build option, I think, if I remember correctly from the real-time Linux workshop. So that idea of dedicating one core to a task, we're not the only ones on that idea. At the real-time Linux workshop last week in Graz, there were about 2 or 3 papers about this theme, and there are various ideas about going about them. So and the support in the Linux kernel for that is improving. There was done work at Siemens to separate out a core and to boot something like RTOS, free RTOS or RTEMs in that. It's almost like a VM. However, it is much simpler and more close to the hardware. The reason why these folks wanted it, to have a second operating system for safety concerns. So that comes mostly from the autonomous driving, from that background. To have a second operating system with a completely separate software history and background. So there are some changes coming into our direction which help with that. That thread function, that's something which we discussed yesterday, Alex and me, that such a busy looping thread can actually be used as event-triggered execution of threads. Because now, since you're running on a POSIX thread, you could just use any Linux API to wait for an event, like the event file descriptor, or wait for a pin, or what have you, and have triggered execution. The only external package which has been which we brought in this merge in this code base is from concurrencykit.org. And if anybody is interested, I really recommend it. It is done by people in the know, and it is. I followed Charles' advice here. If you don't know it, just copy it. Use
the library.
Yeah, use the library. Yeah, use the library. It's interesting to see where these guys which use that code come from. It's us from machine control coming into this. It's the high-frequency traders, which did in the past contribute a lot, and it is the online ad brokers. The guy behind the concurrency kit is the CTO of an ad broker company. So that's where the need for these high-performance algorithms comes from. Okay, this is not ready for a merge, but a couple of weeks away. If you really want to dive into it, there's a link to that branch. what changes come out of this, I think we've half-heartedly we've done so as if the Raspberry 1 actually works with Machine Kit. Well, it doesn't. At this stage, we'll really have to dump it because it's an ARM6, and it cannot do 64-bit atomics. So we'll have to cut that, and we actually have to remove that from the website. Thankfully, though, there's an quite good RT preempt kernel coming for the Raspberry 2. So if somebody just loves that platforms for reasons which I cannot understand, then there's a way to do that, and it is actually an ARM7 core, so it is usable. The core code is done. Introducing the new API layer needs some cleanup work. Nothing on the semantic, but mostly header editing. And we need to decide on how to merge this in the light of in the steps which we discussed yesterday going forward. And if we separate the CNC stack from RT and at which stage they merge. But I'm confident that this doesn't break anything. You can actually, just to make sure you believe me, that is, well, similar to config, but that's running all on HAL v2. It's an unchanged configuration. So for that part, it actually works. So that's where we are with the multi-core support. Thanks for your attention. Any questions?
That integrates nicely with the, is it HALmk, or what is the name for the?
I don't get it.
Oh. So the version 2 API, that also will talk remotely with it'll have the Python binding.
Those have been changed already. The Python bindings are all upgraded for v2.
About the HAL-MultiKore layer, we'd be able to actually make like a thin client, run HAL remotes as far as a secondary or distributed setup.
If I understand your question correctly, that is about bridging HAL instances?
Could it be? HAL remote layer.
Yeah.
So you can actually have like a thin client, like a tablet or a Raspberry Pi, using just the GUI and actually having a data layer between the two, so that the back end and the real time is handled like on something other than the Raspberry Pi.
Oh, well, that always was the plan to have that. It actually works. So that's that was the first demo he did. So yeah. Now we do not require the Linux CNC stack for the UIs plus HAL to run.
Okay.
They run standalone just fine. You need it once the motion component and IO control comes into it, but not before yet.
Okay, thank you.
The only other thing I might mention is there's a lot of talk about 64-bit atomic. The 64-bit value has to be aligned for 64 bits to be atomic.
The memory allocator plus the compiler's structure alignment restrictions guarantee you that. So, but yes, in some cases I've explicitly aligned and actually padded data structures to make sure they are alone. But that is not on alignment, it's about false sharing actually. Yeah. That is not an issue. The shared memory allocator does alignment and optionally cache line alignment, in case you want to keep false sharing out at the allocator level. So I'm thoroughly confused and made sleepy just about everyone. So happy to stop at this point.
we're going into the next talk.
Oh, this is the lunch break.
Excellent.
Ooh.
Oh, that's true.